My project is extreme adverse vehicle vision. The problem statement is that object detection is crucial for autonomous systems like self-driving cars, but performance degrades significantly under adverse weather conditions, such as fog, rain, snow, and sandstorms. This degradation occurs due to reduced visibility, noise from weather patterns, and lighting variations, posing serious safety risks. My project addresses the challenge of developing robust object detection a system that maintains reliability across diverse weather conditions. For data, I combine two datasets, Dawn, which contains 1,027 real-world traffic images captured under various adverse weather conditions, and Wedge, which consists of 3,360 images featuring synthetic weather conditions applied to driving scenes. After processing and filtering, we use 3,360 image annotation pairs for training and evaluation. Previous research shows two main approaches, training on real all-weather data and using synthetic weather augmentation. Gupta et al. Found that training models on large, diverse real-world datasets yielded the best performance when tested on unseen adverse weather images. Synthetic data generation using style transfer networks was also effective, but generally performed worse than real data. Our, our data processing pipeline involved merging and standardizing both datasets, converting annotations from XML to YOLO format, handling missing files, and creating stratified train validation test splits. During annotation conversion, we identified an issue where van objects were present but not included the class list. We also attempted to address class imbalance through oversampling rare classes, like the bicycle class. For evaluation, we used standard metrics including precision recall, MAP50, and MAP50 to 95. We employed stratified sampling for dataset splitting to ensure proportional representation of different weather conditions and rare object classes. We compared three distinct approaches. The naive approach implements simple methods based on color thresholding, edge detection, and background subtraction. The traditional computer vision approach combines HOG for pedestrian detection, HAR cascades for vehicle detection, contour detection, and SIFT feature matching with non-maximum suppression to merge detections. And the deep learning approach uses YOLO V8N and YOLO V8S, which leverages neural networks to automatically learn features from our merged dataset and benefits from transfer learning. This was the test image that I used, and this is the naive approach results. We can see that it did not detect the objects very accurately. This is the traditional approach with the confidence measures, and this is the deep learning approach. So the YOLO V8S model achieved an overall MAP50 of 0.506 and MAP50 to 95 of 0.248 on the validation set, with an inference speed of approximately 192 FPS. And we trained this on, I trained this on the V100 GPU. So the deep learning approach significantly outperformed the traditional CV baseline and the naive approaches. And during training, we faced two main challenges. We encountered class imbalance, so the bicycle class wasn't being detected properly, with the models struggling and showing zero recall, and the initial exclusion of the van class, which needed further assessment. I know it says YOLO V8N, but I did the training both on the nano model and on the small model. After evaluation, the YOLO V8S was selected as a primary model. Despite requiring GPU resources, it demonstrated substantially higher accuracy compared to the traditional naive approaches. The naive method proved highly sensitive to variations in lighting, color, and weather effects, making them unsuitable for robust real-world object detection. So in conclusion, the deep learning with YOLO V8 S proved most effective for object detection in adverse weather. Combining real and synthetic data sets provided valuable training research, and for future improvements, should focus on addressing the class imbalance and incorporating all the object classes, and potentially using a larger model um, when resources permit. From an ethical perspective, this is a safety critical application where failures in adverse weather can have severe consequences. The data sets may contain inherent biases related to the geographical location, time of day, and vehicle types. When YOLO V8S is a black box, while YOLO V8S is a black box, applying explainability techniques like BODEM helps understand model decision making and identifying potential failure modes. The project attempts to mitigate risks by using diverse data evaluated across weather conditions and planning explainability uh, analysis. Now, as for the demo, so because generation takes 2 minutes, I've preloaded this. So a test image can be loaded here. And then we click on generate explanation. And this image with the confidence scores is shown. And this is the saliency map, which shows us which parts of the image influence the model's detection decisions. So brighter areas in the saliency map on the right side indicate regions that were more important for the detection. Thank you.